And in the last video, we looked at how we can think about bonding and antibonding orbitals if we're constructing those molecular orbitals from s orbitals, okay? But what about p orbitals? So in this case, right, remember, like we have the p orbitals lie along the axes, the x, y, and z, okay? And so they all look like this, and they are differentiated depending on how they align along the x, y, and z axes, okay? And so, for instance, if we think about, so we're going to define quickly this as a z-axis, okay? And let's say we have two p orbitals that point towards each other on an end-on fashion, okay? And we're going to have the lobes closest to each other match in sign, okay? So as these approach each other, right, because these are in phase, we're going to have constructive interference, okay? And so one important thing to remember is that where the nucleus is right here within the nodal plane of the p orbitals, okay? And so if we think about constructive interference between this, right, what we expect is we're going to have an increased electron density in the molecular orbital between the two nuclei of the resulting MO. And so if we think of that, right, what we end up with is we still have these nodal planes. Right, and we have a resulting bonding orbital between these two PZ orbitals. Okay, and much like what we had, the situation we had with the s orbitals for hydrogen, right? We can draw a line through the two nuclei, right? And we have a rotational axis. So not only do we have a bonding orbital, but it also has sigma symmetry again. Okay. All right. If instead we have destructive interference, okay, where the phases, where the lobes pointing towards each other for these two PZ orbitals are not in phase, right? Then we're going to get something that's higher in energy than the bonding orbital, and what we expect to see is that we're going to have a node between the two nuclei, right? Much like we did for the antibonding orbital for dihydrogen, right? So this is our nucleus, right? Again, notice that there's a nodal plane here. Right? That bisects the area between the two nuclei, okay? And that's going to be indicative of an antibonding orbital. And again, this is going to be a sigma antibonding orbital. Okay? But remember, right, that we also have other p orbitals. Now let's say, instead of the z-axis, we think about these on the x-axis, in which case, right, we can think about two px orbitals, px for atom A, px for atom B, right? And then we're going to define the phases of the lobes. In this case, right, they're not pointing towards each other, okay? So we expect that there's going to be these are going to overlap in a different way. And in fact, that's exactly what we end up with. And so in this case, right, what we end up with is constructive interference, right? We end up with, these are two nuclei, we get a lobe this, lobe like this, okay? But again, there's density, right, between the, there's density in the regions where there wasn't before, right, between the two nuclei, okay? So this is still a bonding orbital, okay, but the symmetry is very different, right? So in this case, right, we have a mirror plane, right, which we can also think like takes the same space as the nodal plane, right, between the two lobes, right? But we have this mirror symmetry, right? And what we call this is a pi bonding orbital. Okay? Now, what would we have for the antibonding? Constructive. All right, what would we have for the destructive? All right, so for that, right, we would have to flip the signs of these lobes. In this case, right, we don't expect to have this accumulation of electron density. And what we'd end up with is something like this, where we not only have the nodal plane here that intersects with the nuclei, but we now have a second nodal plane that doesn't exist in the bonding orbital, right? So we have a second nodal plane here, and this is going to be a pi antibonding orbital. Okay. And in the next video, we'll discuss what the energies of those look like relative for the sigma bonding and antibonding orbital versus the pi bonding and antibonding orbitals. And so one thing to remember here, right, that we didn't consider is that there's also a py orbital, right? And so what all that happens here, right, is that that is going to look like, so this is our axis, or z-axis. And so that's going to be similar in shape to our bonding, our pi bonding and pi antibonding orbitals that we formed from the px orbitals, except they're going to be rotated 90 degrees. All right. And so what we have here is what we end up with is degeneracy between the energy of these, because the only difference between the bonding orbital, for instance, derived from atomic px orbitals and those derived from the py orbitals is just a rotation in space. And so there's no real energy difference between those two. And so what those end up being is a degenerate set of orbitals. So there's a set of pi bonding, there's a pi bonding orbital resulting from the px atomic orbitals, and there's a second degenerate set resulting from the py orbitals.